Get ready to dive deep into the really fascinating edge of artificial intelligence today.
Yeah.
We're looking at these models that are getting unbelievably good at something quite ambitious,
Hmm.
not just understanding images, telling you what they see, but also turning around and actually creating new images or editing the ones that are there, and all inside one system.
Exactly. It's this long-standing goal, really, building AI that can genuinely perceive and create visual stuff seamlessly.
Right.
Because historically, models tended to focus on one or the other, didn't they? Either the vision, understanding side, classifying things, captioning,
Like see,
yeah, seeing, or image generation like your text-to-image diffusion models, create.
creating.
But putting those two halves together into one fluid system that, crucially, doesn't kind of drop the ball on either capability. That's a huge technical hurdle. And honestly, a really exciting academic puzzle, too.
Yeah, it feels like wanting, I don't know, one tool that can read this really complicated visual scene, and then based on what it saw and what you tell it, it can paint a completely new picture or make smart edits.
Precisely.
And you've brought us a fantastic source today, this new Arxiv paper. It's called BAGEL, Building a Generalized Language Image Model.
Yep, that's the one, BAGEL. So our mission for this deep dive is, well, to really get under the hood, academically speaking, go beyond just the buzzwords.
Okay.
We want to unpack the key technical innovations behind it, look at the architecture choices they made, understand their training strategy, and see what its performance actually tells us, especially any creative steps forward or, surprising results. What does this mean for the future of AI that can see and speak?
Excellent. I've got the paper right here. Let's dig in. So you mentioned this core challenge, unifying understanding and generation. According to the paper, how have people usually tried to crack that nut before BGEL?
Right. So the paper lays out basically three main families of approaches that researchers have explored.
Okay, lay them out for us.
First up, there's what they call the quantized autoregressive approach, or AR for short.
AR. Got it.
Think of this like taking images and breaking them down into little discrete pieces, visual tokens, kind of like how text gets tokenized into words or subwords.
Ah, okay, like pixels and her words.
Sort of, yeah. Then you use a standard large language model, an LLM, usually a decoder-only one, and you train it to just predict the next token. Doesn't matter if it's a text token or one of these visual tokens.
So it's treating images almost like just another language, a sequence of tokens.
In a way, yes. And that's appealing, right? Because you can leverage all the powerful machinery we already have for LLMs.
Makes sense.
But, the paper points out, this approach often struggles with the visual quality. The generated images maybe aren't quite as sharp or impressive as other methods can produce.
Uh-huh.
And maybe more importantly, generating images this way is sequential, token by token by token, which makes inference actually creating the image pretty slow.
Okay, so conceptually neat, fits with LLMs, but maybe not the best pictures and definitely slow to generate. What's approach number 2?
The second one is the external diffuser approach. This one's actually really popular right now.
Right.
Typically, you have a language backbone, could be a standard LLM, could be a multimodal one, a VLM, and you connect it, usually through some lightweight adapter layers, to a separate powerful diffusion model. And that diffusion model handles the image generation part.
Okay, so the language brain think about the request, maybe looks at an input image, and then it sort of tells the diffusion painter what to create.
That's a good way to put it. Yeah, the language model condenses the input text, maybe image description, whatever, into usually a small set of latent tokens, a compact representation.
Right.
This compressed info gets passed to the diffusion model, which uses it as guidance to generate the image. The big plus here, often faster convergence when you're training it compared to the pure AR methods. And they can get really competitive results on benchmarks.
Sounds pretty efficient then. What's the catch? Is there a catch?
Well, the paper argues there's a significant one. That very act of compressing the language model's understanding down into just a few tokens. They call that an explicit information bottleneck.
Ah, the bottleneck. Everything has to squeeze through this tiny opening.
Exactly. And when you do that, you risk losing important details, nuances from the original context. Especially, they argue, when you're dealing with really long, complex inputs. Think, multiple images mixed with lots of text.
Like reading a web page or a document.
Precisely. That bottleneck can really hold the model back from doing sophisticated, long context, multimodal reasoning, the kind of reasoning LLMs are getting so good at just with text. So it's seen as potentially limiting how far you can scale these models for understanding really complex interleaved stuff.
Okay, so AR is slow, maybe lower quality. external diffuser is faster, maybe better quality, but has this bottleneck that could limit really deep understanding, especially with long sequences. What's the third path, the one BAGL seems to have taken?
Right. The third way is the integrated transformer approach. This one aims for a much deeper kind of unification. Okay. The core idea is to bring both the language model parts and the visual generation parts together inside one single large transformer architecture.
Not separate models linked together.
No, instead of adapters connecting different models, you have one common neural network structure handling both text and visual information flow.
Like one brain doing both jobs.
Pretty much, yeah. The hypothesis here is that, look, autoregressive transformers are great at understanding, reasoning, handling sequences, and diffusion transformers are really powerful for making high-quality pictures.
Hmm.
So by bringing them together in one unified framework, you ideally get a more seamless, flexible interaction between understanding and generation.
And presumably that avoids the bottleneck problem you just described.
It does. That's the key advantage the BAGEL paper highlights. This integrated transformer approach maintains what they call a bottleneck-free context, all the way through the layers.
Interesting.
This allows for lossless interaction, as they put it, between the parts doing the understanding and the parts doing the generation. They argue this architecture is potentially much better suited for achieving that true multimodal reasoning, for scaling up effectively, maybe even down the line, for things like multimodal reinforcement learning. They sort of speculate on that.
Okay, so it's the bottleneck-free route. Sounds like maybe the hardest computationally, but potentially the most promising for future capabilities. That really sets the stage. So which way did BAGEL go? Was it the integrated transformer?
Yes, explicitly, they went for the integrated transformer solution. The paper makes a really strong case that, based on their experiments, this architecture just holds more promise for learning those richer, more complex multimodal skills, and crucially, for getting those emergent abilities that seem to pop up only at massive scale. They basically see it as the better foundation for tackling the really hard stuff like that long context reasoning across images and text.
That's a big technical bet then, choosing the path that needs more compute but promises maybe deeper integration. So what does the BAGEL architecture actually look like? What's under the hood? What's the base?
So the foundation, the backbone for BAGEL, is inherited from a standard decoder-only transformer, the kind of very common for LLMs. Okay. Specifically, they actually started it off using weights from the QN 2.5 LLM. They mentioned QN 2.5 partly because it's a strong performer, but also importantly because it's publicly available. That helps with reproducibility, lets others build on it.
Right, starting with a powerful open model. So what specific technical tweaks did they make to that LLM base to get it ready for handling images too inside this integrated structure?
Well, they included several standard techniques you see in advanced transformers nowadays. Things like RMS norms, SweeBLU, those help with performance and training stability. Rope, order embeddings for handling where tokens are in the sequence efficiently.
Uh-huh.
And they also use group query attention, GQA. That's a technique to cut down on the computation and memory needed for the attention mechanism, which is super useful when you're dealing with potentially really long sequences that mix text and visual tokens.
Standard high-performance tricks, basically.
Yeah, pretty standard stuff for big models now. But they also added something maybe a bit less common, a specific tweak, QK norm in each attention block.
QK norm, what's the significance of that here?
So the paper notes QK norm is often used in models designed specifically for image or video generation. And its main job here inside this integrated multimodal transformer seems to be helping stabilize the training.
Okay.
Training these huge, complex multimodal beasts can be, tricky. Things can go off the rails. So normalization techniques like QK norm are put in specifically to stop things like the attention scores getting too wild, too unstable, which can really mess up the learning process.
Okay, let me see if I've got this. They took a strong language model core, added standard performance boosters like GQA for efficiency, and then brought in this QK norm, which is common in vision models, just to make sure everything stayed stable when training image and text processing together in one network.
Exactly. They're adapting that language-focused architecture with bits and pieces needed for robust visual work. And for the visual input itself, they use a vision transformer, a VADE encoder.
Mm-hmm.
They started that off using SIGLIP2, which is a very strong state-of-the-art vision model. And they also integrated something called NAVIT.
NAVIT.
Yeah, it's a technique that lets the model handle images at their original native aspect ratios. So you don't have to squash or crop everything into a square, which can lose information or distort things.
Oh, that's neat.
Yeah. And then there's a simple MLP, a multi-layer perceptron acting as a connector. It just maps the output from that VT hearing coder into the same sort of embedding space as the LLM's tokens. That's how the visual info gets plugged into the main transformer backbone.
Okay, so the picture's getting clearer. They didn't just slap things together. Strong LLM base, strong VT setup that keeps aspect ratios, specific normalization for stability, and an MLP bridge, all inside that one transformer.
That's the core integrated structure, yeah. But they didn't stop there. One of the really key academic innovations they explore in the paper is how they actually organize the computation within that transformer. The
Oh.
paper compares a few different ways of setting it up, like a standard dense transformer where all parameters are used for everything, or a typical mixture of experts, MOE.
Right, MOE is becoming quite common.
It is. But the variant they found most effective, and the one that's really central to BAGEL's final design, is what they call a mixture of transformers, or MOTE.
MOT versus MOE. Sounds subtle, but I bet it's important. What's the difference based on what they found?
It's actually a crucial difference. A standard MOE, like you said, is common now. It usually duplicates only specific, smaller parts of the network. Most often, it's just the feed-forward network layers, the FFNs.
Right, the experts are just those FFN layers.
Exactly. The idea is sparse activation, only a few expert FFNs process each bit of data. But the BAGEL paper argues that just doing that, just a standard MOE, wasn't really enough to fully solve the inherent conflict between understanding tasks and generation tasks within their integrated architecture.
Ah, the task conflict.
Yeah, so their moat design, it goes further. It duplicates all trainable parameters for what they call a full-size generation expert. So rather than just having specialized FFNs, they've essentially duplicated much bigger chunks, maybe even entire transformer blocks, to create these parallel pathways. One pathway seems more optimized for understanding, the other more for generation.
Wow, okay, so duplicating the whole expert, or a much bigger part of it. Why is that so significant? How does that help with the task conflict specifically?
Well, the paper suggests that by giving understanding and generations their own, more dedicated sets of parameters, their own pathways, within the same overall model, the model's weights aren't constantly being pulled in opposite directions during training.
I see.
Imagine trying to train just one set of weights to be brilliant at both analyzing an image, what's in this photo, and creatively generating a new one, draw me a purple elephant. Those tasks might need different things computationally. They might learn at different speeds.
Yeah, sounds plausible.
So this mode design, by providing these more separated full-size expert modules within the integrated structure, lets each capability, the seeing and the creating, learn and get strong side by side without interfering with each other quite so much.
Makes sense.
And they actually show some evidence for this in figure 3 of the paper. They plot the loss curves, how quickly the model learns for understanding versus generation tasks, and those curves look different and generally better for the mode version compared to the Density or standard mode versions. So this mode architecture choice is really a core academic contribution here. It's suggesting a specific way to build these unified models so they don't end up being mediocre at both things.
That's genuinely fascinating. It's not just combining them, it's like finding this clever internal structure to manage that inherent tension. Okay, so with this complex, innovative architecture sorted out, how on earth do you actually train a beast like BAGEL? What kind of data, what kind of process does it need to learn all this?
All right, that brings us to their training strategy, and it's definitely not simple. It's a multi-stage process, which they lay out pretty clearly in Table 3 of the paper, not just one big training run, but stages.
Okay, walk us through the stages then.
Stage 1 is alignment. Here, the main goal is just teaching that vision encoder to talk nicely to the language model.
Connecting the eyes to the brain.
Kind of, yeah. They mostly train just that MLP connector we talked about while keeping the pre-trained VOT and LLM weights frozen, or mostly frozen. This stage usually uses image-text pairs, often focused on captioning, and typically at a lower image resolution, just establishing that basic link.
Got it. Stage 1, connect the parts.
Stage 2 is pre-training. This is the monster stage, the big one. Here, they train the full integrated model on a truly massive and diverse pile of data.
How massive are we talking?
Trillions of tokens overall. This includes huge amounts of text-only data. You need that to keep the language skills sharp. Lots of image-text pairs for both understanding tasks like visual question answering and generation tasks like text-to-image. And critically important, a very large amount of what they call interleaved multimodal data.
Okay, hold that thought on interleaved data. What's after pre-training?
After the big pre-training phase comes continued training. In this stage, they typically bump up the resolution of the images the model sees, and they also increase the proportion of that special interleaved multimodal data in the training mix. The idea is to refine the model's abilities with higher quality visuals and expose it even more to those complex, real-world type contexts.
Refining it. Makes sense.
And finally, stage 4 is supervised frame tuning, or SFT. This uses much smaller data sets, but they're very high quality, carefully curated examples. These are specifically designed to elicit the desired behavior for downstream tasks, like generating incredibly detailed images or performing very precise edits according to instructions. This is where they really polish the model's output for specific benchmarks.
Right.
So yeah, this multi-stage approach, it seems absolutely fundamental to getting a model like BAGEL to work well across such a broad range of different tasks.
It really sounds like a structured buildup of complexity. Now, you emphasize that interleaved multimodal data a couple of times. The paper highlights it in gray in their data tables. What is that exactly, and why is it so vital for BAGEL?
Right, interleaved data. It's basically just sequences where text and images are mixed together naturally, like you'd find scrolling through a web page article or in a document or maybe a video transcript where pictures pop up alongside the dialogue or descriptions.
Ah, like real-world documents.
Exactly. The paper mentions they source this from big scrapes of video data and web data. And the reason it's so important is that it gives the model countless examples of how text and images relate to each other in a continuous flow, often over long stretches.
Not just single image, single caption pairs.
No, exactly. It's paragraphs of text, then an image, more text that might refer back to the image or set up the next one, and so on. Training on this stuff is considered really key for developing robust, long context multimodal reasoning, the ability to actually follow a story or understand a document that unfolds across both pictures and words.
So it's learning the narrative thread between the images and text. Wow. That must be an unbelievable amount of data. Did they talk about cleaning it up, ensuring quality?
Oh, absolutely. Data quality is huge, especially at this scale. They detail quite a few filtering methods. They use this in Table 7. Standard stuff like removing UI elements from screenshots, setting limits on resolution, checking image clarity. But also more subtle things, like they tossed out images that looked like documents full of dense, tiny text. Figuring the vision model wouldn't get much from that. They filtered out images that weren't relevant to the surrounding text, using SLAPE similarity scores. They even used LLMs to trim irrelevant headers or footers from web documents, and filtered documents based on how many images they had to avoid contexts that were too image sparse or maybe too overloaded. That kind of curation is crucial.
That's pretty rigorous cleaning. And speaking of data, there was something else really interesting in the paper. They created synthetic training data, specifically for text-to-image generation.
Yes, this is another neat sort of academic contribution and a pretty creative step they took. They actually used other powerful AI models, specifically the big QN 2.572B LLM and the FFUX Tot1-Dev generation model to generate new training examples for BAGEL.
Okay.
But it wasn't just the standard, here's a query, here's an image pair. They created triplets, query, reasoning, trace, image.
That reasoning trace part definitely jumps out. What is that, and why include it?
So based on their description and how this usually works, the reasoning trace is like an intermediate step. The original query might be simple, right? Draw a cat on a mat. But the big, powerful Qwen LLM would first generate a more detailed thought process. It might expand the prompt, break it down, maybe describe the scene more vividly, essentially spelling out its reasoning for how to generate the image well.
Like showing its work.
Exactly, like showing its work. Then that more detailed reasoning trace text is fed to the FIUX model to actually produce the final image.
Ah, I see.
So by including this reasoning trace in the synthetic data they use to train BAGEL, they're effectively showing BAGEL how a more sophisticated model might think about and approach a generation request. It's not just teaching it input X leads to output Y, it's potentially training it to internalize a more structured, maybe step-by-step reasoned approach to creating images, guided by that articulated thinking. It's an attempt to bake more complex reasoning into the generation process itself through the training data.
Wow. So using synthetic data to potentially teach the model how to reason about image generation, not just what to generate. That is a really clever technique. Okay, so we have this carefully designed, bottleneck-free architecture, the innovative MUT structure inside, and this really sophisticated multi-stage training using massive curated data, plus this reasoned synthetic data. How does Beijing actually do? How does it perform against other models out there?
Right, the results. Let's break it down. First, on image understanding tasks. That's in Table 4. BJGel, especially their main 7B MOX variant, does exceptionally well here. Okay? It significantly outperforms other unified models that also try to do both understanding and generation on key benchmarks like MMU and MMVet, sometimes by really large margins.
Better than other unified models. Got it.
Yeah, but maybe even more impressively on these understanding benchmarks, BJL actually competes strongly with and sometimes even beats specialized understanding-only models at similar sizes. Models like QN 2.5 VL or Interd VL 10.5.
Wow.
And that's really strong evidence, academically speaking, that their mode design and the whole integrated architecture thing worked. It seems to have successfully managed that task conflict, allowing BAGEL to reach state-of-the-art understanding, even though it was also trained heavily for generation. That's a big validation of their approach.
That really is a key finding. Unification doesn't automatically mean compromising on core skills. Okay, what about the other side of the coin? Generation.
For image generation, they show results in Table 16. And again, BJL performs very well. It gets high scores on benchmarks that test things like, did it draw the objects correctly? Is the composition right? Did it handle colors and positions as requested?
The creative side.
Exactly. And it competes strongly there too. It's right up there with leading generation-only models like FLUX.1-Dev and SD3 Medium, and also other top unified models like Genus Pro and MetaQuery XL.
So really strong on both understanding and creation, not just leaning one way. What about editing images, taking an existing one and changing it?
Yep, they looked at that too. There are results for editing benchmarks like EditBench in Table 7 and some nice visual examples in Figure 9. BNGL performs well on editing too. It can handle things from simple object swaps or modifications up to more complex scene alterations. And again, it competes well with models that were maybe even specifically designed just for editing, like Step 1X Edit.
Okay, understanding, generation, editing, it seems like a genuinely strong all-rounder thanks to this unified design. But you mentioned emergent abilities earlier. This is where it gets really exciting, right? Did they find things the model could do that seemed to just appear after enough training?
Yes. And this, for me, is one of the most fascinating and academically significant parts of the paper. They actively looked for these emergent behaviors capabilities that you don't explicitly train the model for, but which seem to just arise once the model hits a certain scale and complexity.
Okay.
What they found was that tasks demanding both understanding and generation, particularly what they call intelligent editing, tasks where the model has to really reason about the image content to make a smart change or create something new based on it, these tasks learn much, much slower during training compared to simpler tasks.
Right, they're harder.
They're harder. But, crucially, as they show in Figure 7, these complex, reasoning-heavy tasks only started showing real improvement, real signs of intelligent reasoning, after the model had ingested an absolutely massive amount of data, around 3.5 trillion tokens, according to their plot.
3.5 trillion tokens?
Yeah. Before hitting that point, the model might just fail on those tasks, maybe just copy the input image, or generate something random if the instruction needed too much inference.
Okay, so what happens after 3.5 trillion tokens? Give us that striking example they used.
Okay, the example they highlight is based on the prompt. A man is standing beside a female brown bear and its cub. Generate an image to show what will likely happen.
Ooh, okay. That definitely requires some reasoning.
It does. You have to understand the scene, understand the typical behavior of mother bears, and then generate an image showing the likely outcome.
Right.
So before that 3.5T token threshold, the model might just redraw the input scene man, bear, cub standing peacefully. It doesn't infer the danger.
It just takes it literally.
Exactly. But after crossing that massive data threshold, the model generates what they call a coherent and semantically appropriate edit,
Meaning?
meaning it draws the likely, albeit rather grim, outcome. The generated image depicts the man being attacked or maybe chased off by the protective mother bear.
Wow.
So the model isn't just following the literal words anymore, it's reasoning about the situation, using the vast world knowledge embedded in its training data, inferring what's likely to happen, and then creating a picture that visually represents that inferred outcome, that kind of inference-driven generation, combining understanding and predictive reasoning. That seems to be an emergent skill, directly tied to hitting that massive training scale with complex interleaved data.
That is genuinely impressive, learning common sense prediction and visualizing it. But okay, even with these emergent skills, no model's perfect. What are the limits? Where does BAGEL still stumble, according to the paper itself?
Right, and they are pretty upfront about the challenges. They show failure cases in Figure 17, like pretty much all current top models. BAGEL still has trouble with certain really hard things.
Such as?
Things like reliably generating very specific trademarked or copyrighted characters, getting Mickey Mouse exactly right every time. Actually rendering complex or long bits of text inside the generated image is still hard. Depicting really intricate or unusual human poses can be a struggle. And precise object swapping. They show an example where it gets confused trying to swap a blue bottle and a red bottle correctly.
Hmm.
It also finds it challenging when you ask it to change Many, many instances of an object all at once in a complex scene.
So the really fiddly details, complex layouts, specific IP, and large-scale coordinated changes are still tough nuts to crack.
Yeah, those seem to be the current frontiers where improvement is needed. And they do note that in some of the tricky failure cases they showed in that figure, another model, GPT-4o, actually performed a bit more consistently. So that highlights areas where BAGEL, and probably others too, still have room to improve.
And did the researchers suggest how they might tackle these limitations going forward?
They did. They suggest a few potential paths. One is just continuing to scale up the training data even further, maybe specifically finding more data that has images containing complex text, for example. Another is increasing the model's overall size, its capacity. And a third is potentially using post-training methods like RLHF reinforcement learning from human feedback.
Right, using human ratings to fine-tune it on those specific tricky cases.
Exactly. Get humans to tell it which attempts at complex text or intricate poses are better, and use that feedback to nudge the model in the right direction.
Okay, keep scaling data and model size and use human feedback for the really tough stuff. Makes sense.
Pretty much, yeah.
All right, so we've taken a really deep dive into this BGEL paper. We've looked at its innovative core idea, that bottleneck-free integrated transformer architecture. We explored their novel use of that mixture of transformers, the MOT variant, which seems really key to letting it be good at both understanding and generating without compromise. And we saw just how critical that sophisticated multi-stage training is, especially using huge amounts of that interleaved multimodal data and even that clever synthetic data with the reasoning trace baked in.
That sums it up nicely. And the results show it works, right? Strong competitive performance across the board, understanding generation editing, particularly impressive on the understanding side for a unified model.
Definitely.
And maybe most importantly, it gives us this compelling evidence for emergent abilities appearing in complex reasoning tasks, but only after hitting truly massive training scales. Trillions of tokens.
Yeah, and while the paper is honest about the remaining challenges, generating specific characters, handling fancy text, complex multi-object edits via GL, really does feel like a significant step both academically and engineering-wise towards these truly general perfect AI models that can fluidly see, think about, and create visual content.
It definitely pushes the boundaries on how we think about designing and training these unified multimodal systems. And that finding about complex reasoning only really kicking in after 3.5 trillion tokens. It raises a pretty fundamental question, doesn't it, for researchers and really for anyone watching AI develop?
Which is,
Well, what other capabilities, maybe ones we haven't even thought to look for yet, might be quietly emerging in these huge unified AI models as we keep scaling them up, keep feeding them more and more diverse data? And how are we even going to discover the full extent of what they can actually do?
that is definitely something to chew on as you encounter AI out there in the world. Thanks for joining us for this deep dive into BGL.